In this video, we'll consider the amount of work done by a constant force. So, for example, if we ignore this picture for now, we'll come back to it. If I ask how much work is done when lifting a 200 gram mass a distance of 0.05 meters, that sounds like a question from last semester. We know how to do those. So if this were last semester, and we asked this question, I have a 0.2 kilogram mass, I lifted up 0.05 meters, how much work was done? We'd say, well, I know work is force times the distance times the cosine of the angle between the force and the distance. So, free body diagram. We have gravity pulling down, and then me pushing up. So if I put my hand here and lift it up, that would be some normal force. So work would be that normal force times the distance times cosine of the angle between the force and the distance. So distance, it's moving upward, and the force is upward. So the angle between up and up is 0 degrees. Cosine of 0 degrees is 1. So it's just that normal force times d. And if we assume it's not accelerating, just moving at a constant rate, then N is equal to mg. So this should just be m times g times d. 0.098 joules. Okay, so if that was a Physics 1 question, why are we asking it again in Physics 2? Now it's time to go back and look at this piece of equipment. So what this is, we've got some mass up here that's connected to a piston down here, which is inside a cylinder. Now that cylinder has gas in the bottom that's connected to a tube that goes over here to a can. I actually have one of them right here. I'm going to get rid of this can right now. I can just add more gas in. So just increasing the number of molecules. So I'm just going to blow into this and you can see what happens here. So you can see when I blow into here, there's a force on the bottom side of the piston, and that force on the bottom side of the piston pushes the piston up. Now there's that force acting on the area of the piston, right? So force acting on an area, that's a pressure. So that pressure of the air is pushing upward and lifting this. So now we're going to look at this not in terms of the force, like a normal force we had last time, lifting this up, but we're going to look at a pressure lifting it up. And we'll see how much work is done by the gas inside here because of that pressure. Okay, so now what I've done is I've added a new drawing. So this time, instead of having a normal force pushing up, gravity down on this thing, I've put this here on a piston. The piston, inside here, there's a certain area inside this cylinder. So I've got this area of the piston, I've got a pressure here, and this is going to go up, again by the same distance. And if this goes up by 0.05 meters, then the piston also goes up by 0.05 meters. Alright, so now, can I take this pressure area and change in height there and find the work done using these? So I know that work was force times distance times, well, we've got the cosine of theta, right? And theta will be exactly the same. It's moving up the same direction as that pressure is pushing it up. Force, let's see, pressure is force per area, right? So force is whatever this area is times the pressure. Okay, so I can replace this force with area times pressure. So right now I have area times pressure times d. If I want to do this in terms of gas, you normally don't think of gas as having an area and a distance. You think of it as having a volume. Well, what is the volume of the gas here? This, I have an area, and then this change in height here. So this is like a delta H if I look at that, so I've got an area and some height, the volume is area times the height, right? Look at this, area times, that's what that D is. So P times V. And in fact, this isn't the volume of the entire cylinder, it's just the height h that it goes up. So it's actually the change in V. So the work done is pressure times change in volume.